Today we'll study number and letter series in the cat way. We'll start with the fundamentals and build our way up to the complex patterns you can expect on the exam. Specifically, we'll look at arithmetic and geometric progressions, both with numbers and letters, mixed series, which combine operations like multiplication and addition, alternating or interleaved series, where two or more patterns are woven together, special pattern series, including those based on Fibonacci logic, perfect squares, and even the sum of a number's digits. Let's begin. Type 1. Arithmetic progression. Series is 4, 9, 14, 19, 24, blank. We have to find the correct number to fill in the blank. Think. Alright, let's break this down. The first thing to check is always the simplest relationship, the difference between consecutive numbers. Let's map it out. 9 minus 4 equals 5. 14 minus 9 equals 5, and so on. The pattern is crystal clear. We are simply adding 5 each time. This is an arithmetic progression. To find the next term, we just add 5 to the last known term. 24 plus 5 equals 29. The blank should be 29. Key takeaway? Always check the first differences quickly. If they are constant, that's your pattern. If not, you can then check for second differences or other patterns. Type 2. Letter series as arithmetic progression. Series is BEHKN blank. Think. Here's the approach. Letter series problems are almost always number series problems in disguise. The key is to convert each letter to its numerical position in the alphabet. A equals 1, B equals 2, C equals 3, and so on, up to Z equals 26. Let's do the conversion. B is the second letter. E is the fifth letter. H is the eighth letter. K is the 11th letter. N is the 14th letter. Now our series is 2, 5, 8, 11, 14, blank. This is much easier. Let's check the differences. The pattern is a constant addition of 3, so the next number is 14 plus 3 equals 17. The final step is to convert this number back to a letter. The 17th letter of the alphabet is Q. So, our learning from this is, for letter series, immediately convert letters to their numerical positions and look for the numerical pattern. Type 3. Alternating series. Series is 2, 5, 6, 9, 10, 13, blank, blank. Think. Let's crack this one. At first glance, the pattern seems chaotic. The jump from 2 to 5 is plus 3, then 6 is plus 1, then 9 is plus 3, then 10 is plus 1. The pattern seems to be plus 3, plus 1, plus 3, plus 1. While this works, a more robust way to see this is by splitting the series into two alternating tracks. This is a common cat pattern. Track 1, odd positions. This track consists of the first, third, fifth, etc. terms. Series 2, 6, 10. Pattern: the difference between 6 and 2 is 4. The difference between 10 and 6 is 4, so we are adding 4 each time. Next term, 10 plus 4 equals 14. Track 2, even positions. This track consists of the second, fourth, sixth, etc. terms. Series 5, 9, 13. Pattern: the difference between 9 and 5 is 4. The difference between 13 and 9 is 4. This track also adds 4 each time. Next term, 13 plus 4 equals 17. So, the two blanks are filled by the next term of track 1 and then the next term of track 2. The answers are 14 and 17. So here's our learning from this. If a single rule looks messy or inconsistent, try splitting the series into 2 or even 3 alternating tracks. Check each track for its own simple pattern. Type 4. Mixed exponential series. Series is 3, 7, 15, 31 blank. Here are the options. Think. Here's how we solve it. Let's try our first method, checking differences. 7 minus 3 equals 4. 15 minus 7 equals 8. 31 minus 15 equals 16. The differences are 4, 8, 16. These are doubling each time. 4 multiplied by 2 equals 8. 8 multiplied by 2 equals 16. So the next difference must be 16 multiplied by 2 equals 32. The next term would be 31 plus 32 equals 63. There is another, often faster way to see this pattern. Instead of just looking at the difference, look at the multiplicative relationship. How do you get from 3 to 7? 3 multiplied by 2 equals 6. That's close. 6 plus 1 equals 7. Let's test this rule. Does it work for 7 to 15? 7 multiplied by 2 plus 1 equals 14 plus 1, which equals 15. Yes! Does it work for 15 to 31? 15 multiplied by 2 plus 1 equals 30 plus 1, which equals 31. Yes! The rule is multiplied by 2, then add 1. Let's apply it one more time. 31 multiplied by 2 plus 1 equals 62 plus 1, which equals 63. Both methods lead to 63, which is option A. The principle here is, if the series grows very quickly, look for a multiplicative pattern, like times x plus y, or an exponential pattern, like powers of a number. Type 5. Mixed letter number series. Series is A2, C4, F7, J11, blank. We have to fill in the letter and the number. Think. Here's the breakdown. This is a mixed series with two independent tracks running in parallel, a letter track and a number track. We just need to solve them separately. Letter track. Convert to positions. 1, 3, 6, 10. Look at the jumps. The pattern of the jumps is plus 2, plus 3, plus 4. The next jump must be plus 5. Apply this to the last letter. J, position 10, plus 5 equals 15. The 15th letter is O. Number track 2, 4, 7, 11. Look at the differences. The pattern of the differences is plus 2, plus 3, plus 4. The next difference must be plus 5. Apply this to the last number. 11 plus 5 equals 16. The next number is 16. Combining the two results, the blank is O16. So the core idea is, in mixed series, letter number pairs, split the problem into separate tracks. Often, you'll find that both tracks follow a similar or parallel logic. Alright, we've covered the foundational patterns. This is a great point to pause and solidify your understanding. On EduRev app, you'll find topic-wise practice tests for LRDI that let you practice specifically on these types of arithmetic, letter, and alternating series. Solving a few of those right now will really help these concepts stick before we move on to the more complex patterns. Let's continue. Type 6 Fibonacci style series is 7, 11, 18, 29, 47, 76, blank. Here are the options. Think. Let's analyze this. Let's start by checking the differences between the terms. 11 minus 7 equals 4, and so on. Look at the series of differences we got. 4, 7, 11, 18, 29. This is not a simple pattern. But wait, these numbers look familiar. They are the terms of the original series itself, just shifted. The difference between 11 and 18 is 7, which is the first term. The difference between 18 and 29 is 11, which is the second term. The difference between 29 and 47 is 18, which is the third term. This means that to get any term, you simply add the two previous terms together. This is a Fibonacci-style sequence. The pattern is solid. To find the next term, we just add the last two terms. 47 plus 76 equals 123. The next term is 123, which is option B. Here is the pattern to spot. If the first differences don't show an obvious pattern, look closely at the differences themselves. Are they part of the original series? This often reveals a Fibonacci-type relationship where Tn equals Tn minus 1 plus Tn minus 2. Type 7, perfect square series. Series is 289, 225, 169, 121, blank. Here are the options. Think. Okay, let's solve it. When we first look at this series, the differences aren't constant. Differences are 64, 56, and so on. The differences are not helping. This is a big clue that we should look at the properties of the numbers themselves, not just the relationship between them. Are these numbers special? Let's see. You might recognize that 289 is 17 multiplied by 17, or 17 squared, and 225 is 15 squared. 169 is 13 squared. 121 is 11 squared. The pattern is now crystal clear. The series consists of the squares of descending odd numbers, 17, 15, 13, 11. The next number in this sequence would be 9. So, the missing term must be 9 squared, which is 81. The blank should be 81, which is option C. Your takeaway from this is, if the differences or ratios between terms are messy, step back and check if the terms themselves are special numbers like perfect squares or perfect cubes. Recognizing them is a huge shortcut. Type 8. Arithmetic geometric series. Series is 3, 8, 16, 21, 42, blank. Here are the options. Think. Here's a solution process. Let's try our usual first step. Check the differences. The differences are 5, 8, 5, 21. That's not a simple pattern. This means a single rule probably isn't at play. Let's look at the operations between each step. How do we get from 3 to 8? We can add 5. How do we get from 8 to 16? We can multiply by 2. Let's see if this repeats. How do we get from 16 to 21? Add 5. It works. How do we get from 21 to 42? Multiply by 2. It works again. The pattern is a repeating set of two different operations. First we add 5, then we multiply by 2. The last operation was 21, multiplied by 2 equals 42. So the next operation in the sequence must be to add 5. 42 plus 5 equals 47. The correct answer is 47, which is option A. The key lesson here is, when no single arithmetic rule fits the whole series, check for an alternating pattern of different operations, like plus x multiplied by y plus x multiplied by y. Type 9. Sum of digits series. Series is 112, 116, 124, 131, blank. Here are the options. Let's figure this out. The difference series is 4, 8, 7. This seems completely random and tells us we need to think outside the box. The pattern must be unconventional. Let's try a weird rule. What if the operation depends on the digits of the number itself? Take the first term, 112. The sum of its digits is 1 plus 1 plus 2 equals 4. What happens if we add this sum to the number? 112 plus 4 equals 116. That's the second term. Let's see if this rule holds. Take the second term, 116. The sum of its digits is 1 plus 1 plus 6 equals 8. Let's add that to 116. 116 plus 8 equals 124. That's the third term. It works again. So, the pattern is confirmed. To find the blank, we apply the rule to the last term, 131. The sum of its digits is 1 plus 3 plus 1 equals 5. So, the next term is 131 plus 5, which equals 136. So our learning from this is, if the differences between terms are completely unpredictable, check for hidden or unconventional patterns. One such pattern is using the sum of the digits of the previous term to generate the next one. We hope that you have understood the concept of number and letter series. Now, here's a secret on how you can study effectively with the EduRev app. You can learn with chapter notes, watch video lectures, and solve CAT-based MCQ tests of this chapter on EduRev.